Okay, in the previous lecture we talked about theorems and definitions, and one of the things about theorems that I told you is that most theorems are conditional statements. If P, then Q. So when you're proving theorems, that's what you're usually doing, is proving a conditional statement, and there's a handful of ways of doing that. I'm going to show you, starting today, what we would call a direct proof of a conditional statement. Okay, let's think about this. You have this statement: if P, then Q. And you want to show that that is true. That's what it means to prove something, is to show that it's true. Now, think about the truth table for P implies Q. It looks like this. So, if you want to show that P implies Q is a true statement, then the first thing to notice is that you don't have to worry about the instances when P is false. Why is that? Because, this is very important, if P is false, then P implies Q is automatically true. So if you're trying to show that P implies Q is a true statement, then you don't have to worry about when P is false, because if P is false, then the statement is automatically true. You have no work to do. Okay, so when you're trying to prove that P implies Q is a true statement, then you only have to consider the possibilities when P is true. Okay, now if P is true, then the only time that P implies Q is true is if Q is true. So this is what we would call a direct proof of P implies Q, is that you assume P is true, show that Q must also be true. Okay, now again, I want to talk about this. What do I mean by assume P is true? Does that mean that we're saying that P is always true? No, it means that if P were false, then we would have no work to do. P implies Q would automatically be true. Okay, so when I say assume P is true, it's because that's the only situation in which we have something to prove. Okay, so for a direct proof of if P, then Q, we start by assuming P is true and show that Q must then be true. Okay, and we're going to do several examples of this because this is crucially important to your success from here on out. Okay? All right, so let's prove this statement. If x is odd, then x squared is odd. Okay. Okay, let's just call this example 1. In the book, which by the way, this is on page 119, it says proposition. If x is odd, then x squared is odd. Let's talk about the word proposition. Hopefully you are reading the book and you would have seen this, but I'll just point it out. Some people use the words proposition and theorem interchangeable. They technically are interchangeable. There is technically no difference between calling something a proposition and calling it a theorem. However, then there are other people who, even though there's technically no difference between a proposition and a theorem, there are people who like to use the words differently, okay? And the difference that they put onto them is that a proposition is basically a theorem that's not terribly important. And when I say not terribly important, what I mean is fairly obvious and easy to prove. Okay, so some people will use the word proposition for things like that, and then they save the word theorem for things that are a little bit more important and take a little bit more work. Okay, so this is a fairly straightforward thing. Okay, if x is odd, then x squared is odd. All right, so we're going to do a direct proof of this. So here's what we do. I'm going to write proof here. And please pay close attention to this lecture. If you develop bad habits now, it is going to be a repeated source of problems for you in your math classes. Because you're going to think you're doing stuff right, but be getting it wrong, and you're not going to understand why. And that's because of developing bad habits at the beginning. It's very hard for students to try to overcome that. You are 100% better off developing good habits from the beginning. Okay? So please pay close attention to this and take it to heart. All right, now, here's my hypothesis. Here's the conclusion. So I start by assuming the hypothesis is true. Okay, so I'm going to write, you can use the word assume. Most people prefer the word suppose. Okay, I'm going to say suppose x is odd. Okay, and there's going to be some work that I need to do. But I want to get down to, therefore, x squared is odd. That's what I want to get to. Okay, now there's a symbol for therefore. I probably showed it to you, but I'm not entirely positive. And that is the symbol 3 dots. Okay, but don't be in a mad rush to use as many symbols as you can. You want these things to be readable. Okay, and in fact, after writing this out, we are actually going to rewrite the final proof in paragraph form. Okay, all right. This symbol is often used to indicate the end of a proof. A little square. Okay, or some people like to write the letters QED, which stands for the Latin phrase quo erat demonstratum, which means that which was to be demonstrated. Okay, all right, now how do we get from here to here? All right, it's called a direct proof, but that doesn't mean you have to go in one direction. You can work from the beginning towards the end, and you can also work from the end back towards the beginning and try to meet in the middle. Okay? So here's what we're going to do. What do we have to go with? Well, the only thing I have to go with is x is odd, and I want to show that something else is odd. So the only thing I really have to use at this point is, what does the word odd mean? Okay, so very, very important to know your definitions. Okay, so I can say that because x is odd, supposing that x is odd, what can I say? Well, what does it mean for x to be odd? It means that x equals 2a plus 1 for some integer a, right? So let's write that down. That's really the only place I can go from here. Then x equals 2a plus 1 for some integer a. And why? Because that's what the word odd means. So I write by definition of odd. Okay. Now where do I go from there? Let's draw an arrow on this side. Where do I go from there? Well, I'm not exactly sure. Well, actually I am, but let's pretend that I wasn't quite sure where I was going to go from there. Then one thing I can do is I could say, well, let's go to the end and let's work our way back a little bit. Well, really, the arrow would be going in this direction. And the question is, where would it come from? Okay, so if I'm going to make the conclusion that x squared is odd, where would that conclusion be coming from? Well, the thing that makes sense is to say, what does it mean to say that x squared is odd? That would mean that x squared equals 2 times an integer plus 1, right? That's what it means to be odd. So if I'm trying to show that x squared is odd, then I must need to show that x squared equals 2 times an integer plus 1. Now I can't write 2a plus 1 because I've already said that x equals 2a plus 1 for some a. So I have set a. I have cemented a. A is the number that I double and add 1 to in order to get x. So x squared cannot also equal 2a plus 1, or else in that case x squared would be equaling x, which means that x is 0. And I have nothing here saying that x is 0, right? It's an odd number. By the way, 0 is not odd, so I would have a pretty big problem then. Okay, so it's important to understand that. I have cemented the value of a here relative to x. A is the number that I double and add 1 to in order to get x. So x squared cannot also equal 2a plus 1, so I'm going to have to choose a different letter. Let's say 2b plus 1. Okay, so I'm going to want to have, before the last line, I'm going to want to have the line then. So we have x squared equals 2 times anything other than x and a. Those two letters have been used. So let's say b plus 1 for some integer b. Let's do this. I'm going to leave off this reasoning here. We'll fill in the reasoning at the end, okay? All right, let's talk about this word then. I said then. Am I saying that because of this, then this is true? No, that would be backwards logic, right? I mean, if I knew that x squared was odd, if I knew this, then this would be true. That's right. But the thing is, I don't know that x squared is odd. I'm trying to prove x squared is odd, which means this is happening because of this. This word then is referring to something that has come beforehand that I haven't filled in yet. You see what I'm saying? If you want to, you could even leave the word then off for now. Okay? Now I need to somehow match these two. They need to match together. Okay? I'm working from both ends, trying to meet somewhere in the middle. Okay? Well, I'll tell you what. How about if we just take this here and let's see. Where could we go from there? Well, if x is 2a plus 1, how about if we figure out what x squared would have to be? Okay? So using the fact that x equals 2a plus 1, then I can say then x squared would equal 2a plus 1 squared. And what does 2a plus 1 squared equal? Doesn't that equal 4a squared plus 2a plus 1? So let's go ahead and write that right here. Notice I'm writing it on the same line. I did not do this. Let me show you. I did not do that. Now, I could have. That would not be wrong. But be very, very careful. Most people, most students write that like that. I'm just looking at this part right here. And they don't understand the implications of what they've written. So, number one, each line in a proof should be a complete sentence. Okay, so if you write that, I want you to notice that it is not true to say that this is a line of the proof, like let's call it line 3, and then say this is line 4. If that's the case, then your line 4 is nonsense, because your line 4 is only half of a sentence. You would not walk up to a person and say equals 4a squared plus 2a plus 1 and have them have any idea what you're talking about. Where's the first half of that sentence? What equals 4a squared plus 2a plus 1? Okay, so again, what's written in yellow is not wrong, but if you think that that's two different lines of the proof, then you're wrong. And you don't really understand how proofs are constructed. And that's going to be a problem in the future. Okay, you have to understand that if you write it like that, which is okay, that is still one line. It is line number 3 of the proof. And it says, then x squared equals 2a plus 1 squared, which equals 4a squared plus 2a plus 1. Do you see that? And did you hear the word which? It's very important. I'm going to read it again. I'm going to read that line to you out loud. Then x squared equals 2a plus 1 squared, which equals 4a squared plus 2a plus 1. Okay? Now, just to avoid the problem entirely, I'm going to put it back the way I had it, because that's why I wrote it that way in the first place, because that is all one line. Why don't we just write it on one line? Okay, now, what am I trying to get to? I'm trying to get to this. X squared equaling 2 times something plus 1, with the something being an integer. And I've gotten this far, x squared equals that. So I have to just somehow rearrange things, hopefully, if I'm successful, so that it says 2 times something plus 1. Well, can't I factor out a 2 from the first two terms and say which equals 2 times, what do you think? How about 2a squared plus a, close parentheses, plus 1. That would be true, right? There's our b right there. Is that an integer? Because it needs to be. Is it? Yes. If a is an integer, then 2a squared plus a is an integer. So doesn't that bridge the gap then from here to here? I think it does. So let's just bump that up to fill in the gap. Now I need a word here at the beginning. A little bit of etiquette, if you want to call it etiquette. This is not a rule, but I feel pretty strongly about it. If at all possible, each line of a proof should start with a word. Okay, so what's missing there? Well, I had it there before. Remember, we were talking about it. It's the word then. Okay, so we are supposing this, then this happens, and then this happens, and then this happens. I'm not just saying then like that's the order it goes in. I'm saying one thing causes the other. And then this happens. And the last then we usually say therefore, because that's our conclusion. Now let's add back in our reasoning. You really want to be in the habit of writing down your reasoning as you go. But since I was working in two directions, then I was writing some lines before the line previous, and so maybe it wasn't clear what the reasoning was going to be. That's why I left it off. So now let's add in the reasoning, okay? So let's talk about every single line individually. So this first line here, suppose x is odd. What's our reasoning for that? Well, that's what we are starting at. That's our starting point. It's not coming from anywhere else. Okay? So you don't have to give any reasoning because it's not coming from anywhere. Some people really want to give a reasoning, and if you do, that's commendable. Your reasoning would be, in that case, by hypothesis. Okay? You don't have, I don't require you to write that, because it's not actually coming from anything previous. It's the first line. There is nothing previous to it. Okay? So you can just say, suppose x is odd. That's our starting point, and that's fine. But if you want to write a reasoning, your reasoning is by hypothesis. Okay? All right, now let's look at the next line. We actually had the reasoning written down there already, so we're just going to end up putting it back. Why do we know that x is then equal to 2a plus 1 for some integer a? Only one reason, because that's what the word odd means. Okay, so that is by definition of odd. Let's look at the next line. Why is that true? Well, that is true just using algebra. It is not usual to write down, you know, all of the algebra steps, because then you're tracing stuff back too far. We don't need to trace back our work all the way back to first grade. Okay, let's just look at it and see all of the things that we did. So technically, what did we use to get from here to here? We used substitution, right? If x is 2a plus 1, then x squared is 2a plus 1 squared, right? And then what did we use to get from here to here? We used the distributive property many times, right? 2a plus 1 squared equals 2a plus 1 times 2a plus 1. And we distributed the 2a over 2a plus 1, and then we distributed the 1 over 2a plus 1. And then we combined. Oh, by the way, that's not even right, is it? It should have been 4a. Sorry. Let's fix that. Which means that next little bit is a little bit off. You probably have been sitting there thinking, when am I going to notice that algebra error? Okay, there we go. Okay, and then how did we get from there to there? We factored out the 2, which is also using the distributive property. And maybe we even use the commutative and associative properties in there somewhere as well. So, you know, the substitution property, the associative property, the commutative property, the distributive property, that's elementary school work. You don't have to write down, I used this property at this point. Basic algebra is taken to be self-explanatory. Okay, if somebody's reading a mathematical proof of a theorem, then you can assume that they know their basic algebra. Okay? So for that reason, we don't need to put a reasoning there, but also there's a little bit more to say about that. Personally, I suggest then, if you are going to be doing some basic algebra, try to have that in lines by themselves. You see, I have got a stretch of algebra there, 3 equalities, and I have them in a line by themselves. And then I stopped that line there. I don't want to add any other logic that is going to need some explanation into the same line where I just have basic algebra. You can. I'm just saying I personally don't, because the algebra is self-explanatory. You still have to write it down. You have to show it, but you just don't have to give the names of all the properties you're using. If I'm going to do anything that is more of a logical step, I'm going to have to explain that, and so therefore I would like that in its own line. I try not to mix that with basic algebra. Sometimes I do, but more often than not. Okay? Now, because of that line, because of line 3, then line 4. But I need to fix it a little bit. Remember, I wrote this line very early on when I wasn't quite sure yet where it was going to be coming from. Now that I filled in that stuff in the middle and I see exactly where that's coming from, I need to add a little bit more to it, which is this. B is something specific, isn't it? So I'm not going to leave it saying then x squared equals 2b plus 1 for some integer b. It's not wrong. I'm just leaving out some important stuff, which is that b is actually something in particular. It's actually this, isn't it? That's the b. So instead of leaving it as for some integer b, let's be specific about that. Let's point that out. And we'll say for, or let's actually write it like this. Let's write x squared equals 2b plus 1, comma, where b is the integer 2a squared plus 2a. Okay, or if you prefer, we could have said where b equals 2a squared plus 2a, which is an integer. You could write it like that, that's fine. Do I need to prove that 2a squared plus 2a is an integer? No, that's very similar to the basic algebra thing, is that you can take it as accepted that the person reading this knows that the set of integers is closed under multiplication and addition, and that if a is an integer, then so is 2a, and so is a squared, which means 2a squared is. And since 2a squared is an integer and 2a is an integer, then 2a squared plus 2a is an integer. You know, again, you have to have some, what's the word? You have to have some sense, which is, there's not a hard and fast rule about this, but you need to learn what's appropriate, what's not enough, and what's too much. Okay? And you need to give reasoning for all your statements, but again, you don't have to chase that reasoning all of the way back to elementary school math. Okay, that's too much. Okay? If a is an integer, which we've pointed out, which is important, we needed to point out that a is an integer. We did that up here for some integer a. We need to also point out, that 2a squared plus 2a is an integer. You don't need to prove that 2a squared plus 2a is an integer. Okay. And then we get to the last one. Therefore, x squared is odd. But what's our reasoning there? We need a reason. Why? Because we have already shown that it equals 2 times an integer plus 1, and that's what the word odd means. So our reasoning is by the definition of odd. Okay. Oh, by the way, to get from line 3 to line 4, I didn't actually give a reasoning, did I? And that's because I didn't make a logical step. All I did was rename something. I just took this and named it b and pointed out that that is an integer. I did not use any rules of inference or anything like that. I didn't use any definitions. You might say, well, didn't you use the definition of odd? No, not in this line. I didn't use the definition of odd. All I did was took the line previous and renamed this with b. I didn't use the definition of odd again until this line. I would like you to think about that and make sure you understand that. Okay, and that's the end of my proof. Some people don't like this. You have your suppose at the beginning, which you can say assume if you prefer, or you could say let. You could say, instead of suppose, I could say let, but then you wouldn't say let x is odd. That's not grammatically correct. In that case, if you use the word let, then the is changes to be. Let x be odd. Okay, I personally like suppose. Some people don't like this. Then. Even this technically is a then, but remember the last one usually we use therefore to indicate that that's our final conclusion. Okay, but previous to that, you see every line starts with a then. Not always, but usually most lines will start with then, and some people don't like that. Sounds repetitive. So what are other words we could use that mean the same thing as then. I'll give you a few of them. Two of them that are very common for people to use are the word thus and the word hence. So you see, you can just pepper those around. Just use then sometimes, use hence sometimes, use thus sometimes. It makes your proof sound less repetitive, a little more formal. Okay. Could you use the word implies? Well, you could, but if you do that, you got to make sure that you're writing a grammatically correct sentence. Let's just pick on line 3. I'll erase the word hence and put implies. Okay, this makes no sense whatsoever. Remember, each line should stand alone by itself as a sentence. If you read line 3 right now, you would say, implies x squared equals yada yada yada. Well, that makes no sense, does it? If I insist on using the word implies, then I need another word in front of it, like this, or something like that. This implies x squared equals. Okay, now that's grammatically correct sentence. So because the word implies mandates that you put another word in front of it, then you're not really saving yourself anything by using the word implies. I would suggest to you to stick with thens, hences, and thuses. And therefores, by the way, therefore doesn't have to be only at the end. You can use an therefore anywhere you want. Okay, so then, hence, thus, therefore. Those are interchangeable. I believe the correct word is synonyms. Okay? Now, why don't we just rewrite that as in paragraph form, just so you can see that. Okay? Suppose x is odd. Then x equals 2a plus 1 for some integer a. I'll go ahead and save a little bit of space and write that this way. You do not have to shy away from symbols, but you know, I'll tell you, in a proof, you want it to be readable. And just as a rule of thumb, you should really have more words than symbols. Okay, there's not a rule about that, it's just a rule of thumb, so you know, take it with a grain of salt. If you write something that is 100% symbols, I'll accept it, and you know, I'll grade it on whether or not it's right based upon what the symbols are saying. Okay, but I think you should have a liberal usage of words in there too. Err on the side of words. Okay, but use some symbols, that's fine. So suppose x is odd. Then x equals 2a plus 1 for some integer a. Oh, I forgot to write. By definition of odd. You could say by the definition of odd. You can even say by the definition of the word odd. But it is commonly accepted in mathematical writing to say by definition of, and then the word that you're using the definition of. Okay. Hence, x squared equals 2a plus 1 squared, which equals 4a squared plus 4a plus 1, which equals 2 times 2a squared plus 2a plus 1. Thus, x squared equals 2b plus 1, where b equals 2a squared plus 2a, which is an integer. Therefore, x squared is odd. by definition of odd. Okay. The goal, what I would like is, I would like for you to eventually be very comfortable writing your proofs in paragraph form. But first, you need to get it down like this. Get it down like that first. That shows that you got the fundamentals. It also makes it easier to grade, by the way. Okay? I'll grade it either way, but make sure you have it in column form first and got that down, and then you can start writing it in paragraph form. All right, let me check where we are in time. Oh wow, that's taken longer than I thought. Let me see if we can do one more, or else we'll just wait. I'll tell you what, let's just end it there. Just maybe go through this again, watch this video again. This is just so important. It's almost like, I mean, I'm not trying to scare you or anything, but it's almost like if you don't get this down, then everything else after this is going to be, you know, useless in a way. Don't give up. If you aren't getting this, don't give up and say, well, then it's hopeless. But I'm just saying that's how important this is. So why don't you, instead of going further, instead of me making this video longer, I'm just going to ask that you watch the video a second time. Okay, we're going to do in the next lecture, we're going to do more practice of proofs.